Okay, so in the last couple of videos we were looking at the concept of work, and we built up some intuition for work and learned a few of work's properties, and then we derived an equation which happens to be up here, the line integral from our starting position to our final position of the force dotted with some minuscule displacement, and we said that we can calculate the work for any force, the work that any force exerts on an object, no matter how crazy it gets, as long as we can define it, over any path, no matter how curvy it gets or how crazy it gets. So what I want to do in this video is to tackle a problem. So a common problem for calculating work looks like this. I have a force field defined. This is a vector field in terms of x, y, so it's only in 2 dimensions, is equal to y comma 2x. And this might look kind of strange, but rewriting it in vector notation might look something like this. Y in the I direction plus 2x in the j direction, right? And that's not too bad, right? So that will be our equation for force. And that equation looks like this. There we go. Alright, so notice that, I'll bring this over here so you can see, we're going from the point 0, 0 to the point 1, 1. We're going to take 3 paths to get there. Alright, so we're going from this spot right here all the way up to here. Alright, and notice that, to start out with, the force is different depending on what spot you're at, right? Depending on what x and what y you're at, then the force will be pointing in a different direction. It will have a different magnitude. The lengths of the arrows describe the magnitude or the strength of the force in whatever spot you are. So over these 3 paths, you'll notice that the arrows are different, right? Over these 3 paths, you'll notice that the arrows are different directions, different lengths and stuff. So intuitively we know that all 3 of the paths, the work done by the force on the object through all 3 of the paths will be different. Right? So that's just a little intuition for you, good visual. So what we're going to do now is develop a game plan. We're going to look at A in this video, the path A that goes along here from 0, 0 to 1, 0, and then from 1, 0 to 1, 1. The first thing I want to do is I know that I already have a force. That force is defined for me down here, but I do not have an R. And usually I want to find an equation for R. That would be like the first step. And my R, usually in terms of time, because you know we're talking about position here. The R is position. So usually in terms of time, when we talk about how something moves over time. So we have x I plus y j. Right? And that's how it's usually defined, and these would be in terms of x as well, or in terms of time as well. Ti plus y of tj. Alright? But in this case, I don't have any t's. I don't have time. I have no information about how fast this object moves along this path. I just have the path. So hopefully when I write things in terms of one variable, I'll be able to do that. So looking at this, I noticed that I can split this path up into 2 parts, from 0 to q and from q to p. So I'm going to do that now. So 0 or O to q. And I'm going to write an expression for the position. I'm going to define R along this path. So I don't have anything for t, but I noticed since we're only moving in one direction, that means that my y value is going to be constant. So I can write things in terms of x, which is good for me. So along this curve, oops, that's a line. Along this curve, we have x is between 0 and 1. Ooh, kind of an angle is that. Good. And then y along this line is just equal to 0. Y is equal to 0. Not bad. So my R, that's going to be in terms of x now. My R in terms of x is just going to be equal to an x in the I hat plus 0 in the j hat direction. Alright. Now that I have that, I'm also going to, before I take any derivatives and figure out what dr is, I'm going to rewrite my force as well with this restriction. So we have y is equal to 0 and x is x, so I can rewrite this with my restriction. F is equal to, maybe I'll do, in terms of my restrictions, so we have x comma 0. X comma 0, so xy, but y is equal to 0. This is a vector. Is equal to, and I have a 0 in the I hat plus a 2x in the j hat. And before I go any further, I want to take a look at what these two break down to. All right, so what I have here is my f of x, or fx. So that would be f in the x direction, and I also have fy. And if you'll remember from the videos before, when we take the dot product, this implies that we're only concerned with the component of force that is parallel to our displacement. Our displacement is in the I direction, or the x direction. So the force in that direction is 0. So it's 0. So no work is done on this object from 0 to q, from O to q. And maybe you can check this out. Along this line, from 0, 0 to 1, 0, all of these lines, all of these force vectors, those are all perpendicular to the horizontal, right? So no work is done. There are no horizontal components of force there are no parallel components of force to the displacement. All right. So writing this formally, I would say the integral from 0 to 1, you'll see that in a sec, of fx in terms of x0, fx of x0 dx is equal to, because x goes from 0 to 1, is equal to 0. Now let's check out the other side, from q to p. From q to p. Q to p. Okay. Now from q to p we also have one-dimensional motion, but this is in the y direction now. So when I go to write everything, I say that x, along this path x is equal to 1. And y is between 0 and 1. 0 and 1. So with that in mind, we rewrite r, and r is now in terms of y. And instead of doing that, I'm going to write it in this form. So we have 1 comma y. Yeah, that's a better way to see. Is equal to, and we have 1 in the I hat direction plus y in the j hat direction. Okay, I'm also going to rewrite my force just like before. My force in terms of 1 y is equal to, and then y is just y, so y in the I hat direction, plus, and then x is 1, and we have 2x over here in the j direction, so that's just going to be 2 j. So we do have a component of force that is parallel to our displacement, so we will have work done here. You can see that. Over here. Right? Along this line, we have there is a parallel component of the force to our displacement. So I'll write the integral of, and we're only really concerned with this guy right here. Hold on. This guy right here is f of y, fy, the vertical component. So what we're going to do is we're going to rewrite this integral. The integral of fy of 1y, which is just 2, fy of 1y, just 2, dy, because in this direction we have y goes from 0 to 1, and it's just a straight line, so if we take the derivative of this, we just have dy. And that's going to equal, well, we have 2 times the integral from 0 to 1 of 1 dy is equal to just 2. And that is my answer. And since joules are the standard unit for work, we're going to make them 2 joules. That's my answer.